So we were discussing about the alkaline earth elements, and here we will discuss about the reactivity towards hydrogen of such elements. Here you should know one thing, that all the elements will react with hydrogen to give the respective hydrides, but beryllium cannot react directly with hydrogen, but there is an alternative by which beryllium hydride can be produced. Let us see. So here beryllium chloride is reacting with lithium aluminium hydride LiAlH4. So this is lithium aluminium hydride, and we will get beryllium hydride plus lithium chloride plus aluminium chloride. So we can say that the beryllium does not react with hydrogen directly to give beryllium hydride, but with beryllium chloride, which is a compound of beryllium, will react with lithium aluminium hydride to give the respective beryllium hydride. All other elements can directly react with hydrogen to give the hydride. Another important reaction is the reactivity towards acids. So the alkaline earth elements will combine with the acid to give the like MCl. M stands for the metals that are present in the alkaline earth element groups. Okay, so M, it can put magnesium also, beryllium also, right? So M is designating all the elements of the alkaline earth metals, plus 2HCl hydrochloric acid. It will give MCl2 plus H2. H2 is the byproduct that is being produced. So after the chlorides, we have studied about hydrides, we have studied about chlorides. Now let us move to the reducing nature, and one important line is there here. Like the alkali metals, the alkaline earth metals are strong reducing agents. So the alkali metals and the alkaline earth metals, both these groups are very strong reducing agents. Okay, so this thing you have to keep in mind. Anomalous behavior of beryllium. Beryllium, the first member of the group 2 metal, shows anomalous behavior. We have studied about it. Anomalous means abnormal. So anomalous behavior as compared to magnesium and rest of the members. Also it shows diagonal relationship to aluminium. Now, why does beryllium show abnormal behavior as compared to the other elements in the group? Because it has exceptionally small atomic and ionic size, and thus do not compare well with other members of the group. So the size of beryllium is very small as compared to the other elements. The other elements are relatively having less difference in the atomic size or in the atomic radius, but beryllium is having very vast difference if you compare with the other elements in the group. So the beryllium behaves abnormally. It has different characteristics as compared to with the other elements of the group. Okay, so because of high ionization enthalpy and small size, it forms compounds which are largely covalent and gets easily hydrolyzed. So the other compounds do not perform in this way. So this is different from the other elements, and we have already discussed about the ionization enthalpy. When we say that high ionization enthalpy is observed, when it is very difficult to remove the outermost electron from the orbit, okay, from the atom, then we can say that it is having high ionization enthalpy. And why does it happen so? Because you see, when the size is very small, no, then the revolving electrons are very close to the nucleus, okay, and you know the nucleus is positively charged, so electrons are negatively charged, so the positive and negative is attracting each other, pulling each other very tightly, holding each other. So it is very difficult to remove the electrons, even though you can remove it by applying high energy, which indicates high ionization enthalpy. But if it is very easy to remove the electrons from the atom, then what happens? You will require less energy, and in that case the enthalpy also decreases. Clear? So high energy means high ionization enthalpy, and low energy requirement means low ionization enthalpy. We have said that there is a diagonal relationship between beryllium and aluminium. So if you try to see the periodic table, what you can see that the beryllium and aluminium are cross to each other, right? So they are not together in the same position, not parallel, but they are one place, one after another, in different groups. So that relationship is known as diagonal relationship. Okay, it is not parallel, but it is like this, diagonal relationship. So let us see what is the diagonal relationship stands for. Like aluminum, beryllium is not readily attacked by acids because of the presence of an oxide film on the surface of the metal. So aluminum is also not attacked by acids, okay, and beryllium is also not attacked by acids. Attacked here means reaction with acids. Aluminum and beryllium, if you put in acidic solution, they will not easily react, they will not easily change in another product. So that is the meaning of not readily attacked by acids. So they both are similar in that case. Now again, beryllium hydroxide dissolves in excess of alkali to give a berylate ion, just as aluminum hydroxide gives aluminate ion. So when beryllium hydroxide is dissolved in an alkali, it will form berylate ion, while aluminum hydroxide will give aluminate ion. So here also similar cases observed. So these two are the important points that you can study for comparing between aluminum and beryllium if they are talking about the diagonal relationship. So these two are the common points you can observe. We will now talk about calcium hydroxide. It is a compound of a metal that is present in the alkaline earth metals. So that is your calcium. Now calcium hydroxide is also known as slaked lime. As you can see here, it's written slaked lime, and the formula is calcium hydroxide. So basically here you will get three reactions which is very important from examination point of view. Let us study a little bit about calcium hydroxide first. So calcium hydroxide can be prepared by using calcium oxide. Okay, so how you can prepare calcium hydroxide, let us see. So when calcium oxide is reacted with water, you will get calcium hydroxide. Okay, so that is a simple reaction. Now if you see here, this calcium hydroxide, when carbon dioxide is passed over it, you will get calcium carbonate, which is the milky substance that appears, plus water. When carbon dioxide is passed through lime water, it turns milky due to the formation of calcium carbonate. Okay, so this is the reaction. Again, when calcium carbonate is passed over excess of carbon dioxide, after this product is formed, more amount of carbon dioxide is passed along with the presence of water which is there. So you will get calcium hydrogen carbonate. First of all, calcium hydroxide will convert itself to calcium carbonate, but if you do not stop the passage of carbon dioxide, if you go on applying carbon dioxide, then what will happen? This calcium carbonate will not remain as calcium carbonate but convert itself into calcium hydrogen carbonate. Now the last reaction is very important here. Milk of lime reacts with chlorine. So this is known as the milk of lime reacts with chlorine to form hypochlorite, a constituent of bleaching powder. So you already know what is bleaching powder, you have seen it, right? So now what happens? When calcium hydroxide is reacted with chlorine, you will get calcium chloride plus calcium hypochlorite, CaOCl bracket 2. So this product, this compound is calcium hypochlorite, and this compound is responsible for the cleansing effect of bleaching powder. So you know that when bleaching powder is spread over a surface, bacteria dies, or means it is done for cleansing purpose, right? So that cleansing purpose, how it comes? Because of this compound, because this compound is present, calcium hypochlorite. So this compound is to be remembered as well as the reaction. And also remember, there are two water molecules produced as a byproduct here. The next important compound that you need to understand is the calcium sulfate, which is known as the plaster of Paris, and the formula is CaSO4 half water. So half water is read as hydrated calcium sulfate. So it means the calcium sulfate is not completely dry, it is not anhydrous, but it is hydrated. Moisture is present in the compound. It is a hemihydrate of calcium sulfate is obtained when gypsum. So remember the formula for gypsum. So gypsum formula is what? CaSO4 to water is heated to 393 Kelvin. So this is the gypsum. Calcium sulfate, two water molecules are present in the calcium sulfate, and when you will heat it, what will happen? Calcium sulfate and water will be will get separated, or you can say one water molecule of four here is there, no, because two gypsum you have taken and here two water molecules, so 2 into 2 4 is there. Out of this 4, 3 water molecule is released, because when we heat any substance that becomes dry, the water molecules are removed, right? When we heat anything, what happens? The water is removed. So here also similar things happening. When gypsum is heated, you know, in gypsum 2 water molecules are there, and since we have taken 2 gypsum, total 4 water molecules is there, out of which 3 water molecule is removed. Clear? And see, if you heat it more, the remaining single water molecule will also be released, and that is known as the dead burnt plaster. So this is the plaster that is produced. Okay, so water is being dried, or water is being removed, and what is left? Only calcium sulfate will be left. If you heat it very extensively, then you will get anhydrous calcium sulfate. Anhydrous means there is no water molecule present, right? And that compound is known as the dead burnt plaster. If you remove the water from this calcium sulfate, what is left? Only calcium sulfate is left, and when there is no water, it is known as anhydrous calcium sulfate, and this compound, this only calcium sulfate compound, is known as dead burnt plaster. So you have to remember this thing, okay? Now if we talk about cement, let us go directly into the important question that is possible here is the constituent. Okay, cement is a product obtained by combining a material rich in lime, calcium oxide. So in cement, the basic compound that has to be present is the calcium oxide with other materials such as clay, which contains silica, SiO2. And the average composition of Portland cement is given here. So calcium oxide, then silicon oxide or silica, then aluminum trioxide. So all these compounds you need to remember. So from here only this question is possible. And what is plaster of Paris? Okay, so that thing you have to remember. What is gypsum? What is dead burn plaster? So this thing you have to remember. And with this chapter is over. This was a little bit lengthy chapter, but since the syllabus is being reduced very much, so this chapter became less, and I hope you have understood this chapter. We will move on to the next chapter tomorrow. Okay.